trying to explain quantum computing in 3 minutes. I was interested in this competition because I really like sharing ideas of science and the little moments of insight where an idea makes sense.
There are a lot of weird things going on in quantum physics, so I wanted to share the exciting research.
Every time I try to talk about what I work on to friends who are not in science, I just find it really difficult, and I thought that this might be a good way to get better at that.
Well, good afternoon, everyone. Well, you are in for a treat. This is one of our main events of the day, the biggest event. We are now at the finals of the world's first Quantum Matters Science Communication Competition. So the challenge is to see who does the best job at making a 3-minute talk that explains some aspect of quantum science or technology to a family audience. And we want you to help us decide the winner. Now, in addition to the Audience Choice Prize, we also have a distinguished panel of expert judges here with us today who will help us crown a Quantum Matters competition champion. So let's go ahead and begin.
I feel like I have to try to make it sort of like a performance, whereas normally in science people will tolerate it if you're not really that great at presenting. I put a lot of hours into preparing for this. It's fairly hard to sort of condense everything into just 3 minutes.
A little nervous, but I think the warm-up session definitely helped, so I'm feeling a bit better.
I did practice a lot, but I hope to finish in 3 minutes.
I'm going to begin by introducing finalist number 1. She is an undergraduate, a senior at Harvard University, majoring in physics and computer science. And in the fall, she's going to be starting a PhD program at Stanford University. And you'll see in just a moment, she has quite a sweet tooth. Let's put our hands together to welcome Jessica Pointing to the stage.
Quantum computing. I have a bag with 100 balls. Each ball has a unique number from 1 to 100. I want to find the ball number 3. Well, on a normal computer, you'd have to pick up a ball, check whether it's the number 3, and then continue until you find the number. This could take up to 100 tries if I have 100 balls. But on a quantum computer, a new type of computer, you could do this in at most 8 tries. And there are other problems that we can solve significantly faster on quantum computers. How is this possible? Well, that's because quantum computers are different at the fundamental level. Normal computers process and store information in bits, zeros and ones. Raise your hand if you like frosted donuts. Okay, me too. So 0 and 1s are just 2 states, like the 2 sides of this donut. Let's say the frosted side is equivalent to 1, and the plain side is equivalent to 0. Quantum computers, however, use quantum bits instead of bits. Quantum bits, also known as qubits, can be 0, they can be 1, but they can also be a superposition of 0 and 1. A superposition is like a spinning donut. When it's spinning, it's neither on its frosted side, and it's neither on its plain side. But how do we actually put this qubit into superposition? Well, we can use quantum gates, which perform operations on our qubits. So this is a quantum gate called the Hadamard gate. If my qubit is on the plain side, I can put it through the Hadamard gate so that it ends up spinning, and now it's in superposition. And there are other quantum gates that perform different types of operations on our qubits. And when we put multiple of these quantum gates together in special ways, like this, you can create a quantum algorithm, which is a set of instructions that you can run on a quantum computer. And these quantum algorithms take advantage of superposition and other quantum effects to work faster. So this is an example of a quantum algorithm called Grover's search. This is the algorithm that can search for the ball 3 faster. So, with quantum computers and quantum algorithms, problems that could take billions of years to solve could be solved in just seconds on a quantum computer. We could use these quantum algorithms to advance artificial intelligence, to design new materials, and discover new medicines. The future is quantum. Thank you.
Let's hear it for Jessica pointing. That was great, Jessica. Thank you.
I think it went okay. People raised their hand when I asked them if they like frosted donuts, so that's a good sign.
Our next finalist number 2, is a graduate student at Harvard University working in quantum optics. And he is developing new quantum information technologies using color centers in tiny diamond crystals. So when he's not in the lab, one of his favorite things to do is go for a walk in the woods. Please put your hands together and welcome Srujan Misala to the stage.
Let me take you to a place where April is warmer. My story begins with the fireflies in this forest and ends with an idea that could make computers more powerful than ever. Now, believe it or not, the flickering patterns these fireflies are showing you are actually very similar to what happens on chips inside computers, phones, and PlayStations. A computer chip is a very complicated object, but the building block for it is something we all know and understand really well. It's just a switch. Now, the switch can either be on or off, like the firefly. So we say it holds 1 bit of information. Computer chips have billions of connected bits, and the algorithms, the apps and games that you run on them take these switches through multiple on-off patterns, specific on-off patterns. Now keep that in mind, because I'm going to walk you now into a more mysterious forest. This is the land of quantum physics. Here, we have switches that can be on and off at the same time. Remember, we're not talking about 2 switches, or just one that flips very fast. This is literally a combination of the on position and the off position. We call it a superposition. Now, of course, the fireflies and switches in our daily lives don't do that. And that's because quantum physics applies only to the tiniest things, like atoms, which make up all of matter, or photons, which are particles of light. Today, I'm depicting these with fireflies. Now, what if you had not 1, but 2 bits, best friends? These 2 can at any time be in one of these 4 patterns in the usual forest. But in the quantum forest, superposition lets them be in all 4 patterns at the same time. If you had some more bits, say a little village of 60 of them, the number of patterns becomes a quintillion. Now, that's a ridiculously big number, but it turns out there are many problems related to inventing new materials and medicines which need computers to process such an impossibly big number of patterns. Trouble with computers today, they have billions of bits, but only in one pattern at any time. Just 60 quantum bits, on the other hand, have enough pattern information to fill up 18 million regular computer memories. And that's why we're playing with quantum bits in our labs these days, encoding them in atoms and photons, trying to make superpositions that could one day make us the most powerful computers. Thank you.
I think it went well. I was a bit nervous, but I think just looking at the kids in the audience made me feel like I was doing this for fun.
And now I'd like to introduce finalist number 3. She is a graduate student in physics and quantum science at Harvard University, and she works with ultra-thin 2D materials, and she studies their special topological properties. Now, she actually grew up close by. She's from Newton, Massachusetts, and she told us that she remembers coming here to the Museum of Science when she was a kid. So please put your hands together to welcome Rebecca Engelke to the stage.
Electronic devices like our phones and computers are getting more powerful, but also getting smaller. As we continue to shrink this technology, we're getting close to the quantum scale, the scale of single electrons. And we can't just make the same type of circuits, but smaller. We're going to need new designs based on different physics. All these devices are made up of electrons flowing through wires of conductive material. In theory, all electrons make it through. But in reality, there are dirt and imperfections in materials that can bounce some electrons out of their path, meaning energy and information is getting lost. If we want to work with single electrons, this becomes a big problem. To study the conduction of a material, we look at its behavior over a range of energies. At the quantum level, even a conductive material has a gap, energies at which it can't conduct. And its conductive energies are called bands. And the science of materials is all about designing or discovering materials that have bands and gaps where we want them. If we want this material to conduct, we could do so by closing the gap like this. But this is not the best way to close a gap, because if we look over here where this piece of dirt is, that can distort the bands and cause the gap to open back up, meaning it can't conduct anymore. There's actually a better way to close a gap, and that involves the concept of topology. Topology is a field of math that describes what shapes can and cannot be smoothly transformed into each other. To say that two things have different topologies means that to turn one into the other, you have to do something drastic, like cut a hole in one of the shapes. For example, suppose I gave you two links of a chain, and I come back a day later and find that they're unlinked. I know nothing about what you did all day, but I do know one thing. I know that at some point you did something drastic to one of the loops. You pried it open. Linked loops and unlinked loops have different topologies, and the power of topology is that it allows me to know that this intermediate state happened. Here I have two materials with different topologies, which I know because the second material, the positions of the orange and blue bands are swapped. If I try to put these materials into contact, the bands want to smoothly connect, but to do so, they have to do something drastic. They have to pass through each other and close the gap, which means that there's ability to conduct right there. The important thing is that if I look where this piece of dirt is, the dirt causes the bands to become distorted, but they still have to cross, so there's still conduction, even if it's a little off to the right. So an electron will find a conductive path through this material no matter what. To compare, in a normal material, dirt causes the electron to bounce out of its path, but at the junction of two topologies, all the electrons can make it through. In my research, I've worked with this material in which the dark and light triangles are two different topologies. Topological materials are an exciting way to control electrons down to the smallest scales. Thank you.
I think it went pretty well. It was fun to see an audience up there in front of me listening.
And now, our last finalist, finalist number 4. He grew up in South Korea, but he visited Boston as a teenager, and he visited MIT, and he decided then and there that he wanted to come back to MIT as a graduate student, and so he has. He's a graduate student in the chemistry department, where he's engineering new ways to induce strong interactions between beams of light. And that has applications in quantum computing. And you'll see in a moment, he's also quite a Star Wars fan. Put your hands together to welcome Joseph Yoon to the stage.
This is my favorite scene from Star Wars, the lightsaber duel. I always wanted to have a real lightsaber like this and wondered how to make one. Today, I'd like to tell you how to make a lightsaber using quantum properties of light. So let's first take a look into the properties of lightsabers. First, a lightsaber must be able to cut through materials, like trees in this movie. How can you achieve this in real world? Well, a powerful laser beam can already cut through steel, like a razor blade or a saw blade. So we can achieve this. Second, a lightsaber has a finite length. Normally, if you shine laser beam, it just propagates forever. But if you use two mirrors to trap light, you can do this. However, the third one is tricky. Lightsabers, they clash, they repel each other. But light normally doesn't do this. This is because normally light beams pass through each other. So in principle, we cannot make a lightsaber. However, quantum physicists have figured out a way to make light beams repel each other. So we've put a single atom between two mirrors and then turned this lightsaber on so that this atom gets excited and becomes larger. And then we've prepared another one, lightsaber 2, and then surprisingly, these two repel each other. So we can go back to the list and check this off. So we can effectively make a lightsaber in a lab, but we don't want to use it to battle our enemies. So we think it will be useful in another way. So we are taking it one step further to have one control the other. If we cross the two lightsabers and turn the lightsaber 1 on, then the second one cannot be turned on. Or if the first one is off, then the second one works again. This means that lightsaber 1 can switch the lightsaber 2 on or off. And this can be used to make a computer, because computers are made of millions of electrical switches that can be turned on or off. But the problem is, this is very inefficient. When electrons go through wires, they generate heat, and that's why our computers get hot. On the other hand, light switches, they are much faster, much cooler, and importantly, they are key elements of quantum computers. So it will allow us to solve problems that are out of reach today. So that's how quantum physicists are working hard to implement their lightsabers into quantum computer. Thank you very much. I think it went very well. Like, the audience liked it. They especially liked the lightsaber analogy.
So now that we've heard all of these fabulous talks, it's time for our judges to go off to deliberate.
I'm blown away. They're taking these very, very difficult concepts, they're making them seemingly simple and enchanting.
I thought that they tackled some pretty tough stuff and they did a pretty good job of explaining it.
Yeah, these presentations were excellent. I've never been able to explain anything in less than an hour. This is what I do for a living, so to do it in 3 minutes was very, very impressive.
I think it's going to be very difficult to make any choices.
And now it's your turn. Your turn to text in your vote for the audience choice winner.
Lillian looked at the stage and said, you know, I didn't think it would be so interesting listening to all the stories, but it really was.
They were really good talks. I feel like I understand more quantum mechanics now.
So there's less than a minute left to get in your text votes. And there we have it. Time is up. I checked the audience choice tallies. Are you ready to hear? Yes. Okay. Well, I am absolutely delighted to announce the audience choice winner for the world's first quantum matter science communication competition is Jessica Pointing. Congratulations, Jessica. Let's make sure we get a photo with your certificate. Let's give a big round of applause for Jessica Pointing, our Audience Choice Quantum Matters winner. So, I understand the judges have come to a consensus. So, Professor Joe Cikelski.
All right.
Was it a difficult decision?
Yes, it was very difficult. It was very hard to decide. We talked over and over, but finally had to come up with a decision, yes.
Do you have any general comments for the competitors?
Yeah, you guys did an excellent job. I don't know how you could fit so much into 3 minutes. The visuals I was very impressed with, but then your ability to communicate slowly and clearly is something I myself aspire to. And I thought also we're very creative in the way you decided to show off some of the really exotic quantum behavior.
Well, thank you so much, Joe. Everyone's on the edge of their seats to find out who is the first place winner of our competition. The winner of the world's first quantum matter science communication competition is Srujan Nisala. Congratulations, Srujan.
Well, I just took a picture of the screen to send my mom because I think it's the closest I'll ever come to being on reality TV. So.
Come on up, all of our finalists up on stage. Let's give them a round of applause for doing a fabulous job. And we want to thank our distinguished panel of judges. Would you please stand up? Thank you so much for judging our competition. Have a fabulous rest of the day here at the museum.